Hi, my name is Daniel Freeman, and I'm here for Mechanics of Materials with my two associates who will introduce themselves now.
I'm Ezra Phillips.
And I'm Angel Ayala.
And today we're going to be presenting on stress and strain. Next slide, please. All right, so we're going to be talking about what stress and strain are today. And even though it's not a very common subject, we really deal with these forces on the daily, to be honest, whether it be in school or in mechanics of materials. But stress describes the intensity of the internal forces acting on a specific plane passing through a point. And there are two types of stress, one being the normal stress, the other being the shear stress. The normal stress would be the stress acting tangent to the surface of an object, and the shear stress would be acting along the surface of an object. The units for these are going to be 1 newtons over meter squared, which is also equal to 1 Pascal, and this is typically what we'll see in problems as well. Next slide, please. So strain, a lot of people seem to think strain and stress are the same thing, when in reality, they're more so related. Now, strain is the force that acts upon an object. Stress is the force that acts upon an object. Strain is the result of that force acted upon. So later on, we'll see what happens as a result of stress, which is what strain is. Now, there are also, just like stress, there are 2 types of strain, normal strain and shear strain. Normal strain is the elongation or contraction of an object in response to normal stress. Shear strain is the change in the angle that occurs between 2 line segments that are originally perpendicular to one another. And typically, strain is unitless. Next slide, please. So, like I said before, stress and strain are related in the sense that strain is caused by stress. So stress is the force that acts upon an object that causes it to elongate or deform, and strain is the measure of that elongation or deformity. Next slide, please. So if we can see that clearly here with the equations for normal stress and shear stress. It's equating a force. We're solving for a force here. And if we go to the next slide, for strain, we're talking about the difference between the original length and the new length, the deformity. Now, with shear strain specifically, I do want to mention that it is a radial difference. So it's going to be the change in angle as opposed to the change in length, which is what normal strain measures. Next slide, please. Now Angel's going to explain some real-world applications for stress and strain.
Thank you, Daniel. As engineers and engineering students, there are many occasions in which we will both observe and interact with stress and strain. It starts very much as engineering students, where the stress of classes gives us a lot of strain within ourselves, but it can also be applied to things like eccentric loading with basketball hoops and billboards, and the intentional use of materials that are either ductile or brittle in order to best perform under different conditions, such as the conditions that you encounter when you're trying to go deep into the sea or high towards the moon. Next slide, please. Some of the more down-to-earth applications are this is more of an example of strain on a block, where the weight of the car here applies a stress to the wooden block that leaves those indents that you can see on the right picture. In the following slide, we will see just a little video of me slowly applying more and more stress to the wooden block as I raise the block to meet the car. So as we go through this, the wooden block goes through its phases of its elasticity, but at a certain point it starts to yield, and that's what leaves the permanent mark on the wooden block. Another real-world example that focuses more on shear strain rather than normal strain is this one. So I don't know if you saw it too well there, but the metal pole bent. However, it bent back into shape because it was still within the elastic zone and hadn't yet yielded because the force of slamming the gate towards the side uh, wasn't enough to cause permanent deformation on this object. And I believe that the next slide is where Ezra will come in.
Awesome. Thank you, Angel. So here is a real-world stress application problem. I will read it to you. It's the beam supports the distributed load with the weight max equal to 4.4 kilonewtons per meters. As shown, the reaction at the supports A and B are vertical, and then part A was determine the resultant internal loadings acting on the cross-section at point D. So right here, this is where we do the calculations. You find the moment at A to find RB, and after all those calculations, you get 4.4. And then to find the I believe that's the final weight, you do 4.4 over the 6 times 1.5, and then that gives you 1.1 kilonewtons. And then you solve for the forces in X and Y. You get the normal force, and then you get VD, and then to get the final, which is the moment at D, you end up taking the moment at D, and then you end up getting essentially 6.19 kilonewtons per meters. And then right here, we have a real-world strain application problem, and then I'll read this as well. The pin-connected rigid rods AB and BC are inclined at theta equals 30 when they are unloaded. When the force P is applied, theta becomes 30.2. And then part A is determine the average normal strain developed in wire AC. So right here, first we calculate the length of AC, and we get 600 millimeters, and then we calculate the stretch length, which then becomes 603.6239 millimeters. And then we calculate the average normal strain, and then by doing that, you do the final minus the initial over the initial, and you get 6.04 times 10 to the negative 3 millimeters per millimeter. And then in conclusion, stress and strain are related, but not the same, as Daniel stated earlier in the above slides. And then also these types of concepts are seen all around us. It's like we said, it's in our everyday lives. And then most materials we will work with do not stray from the elastic region. The elastic limit usually means a failure in that material. And this concludes our presentation. Thank you.
Thank you.
Thank you.